All right, in this video, what we're going to do is we're going to define some of the notation we've been using. So uh, earlier in the example, we used like q adjoin root 2, q adjoin I, q adjoin root negative 2, and so on, and we did in chapter 1 as well. So we're finally going to define that. So suppose you have a subset of C, not a subfield necessarily, not a subring, could be finite even, right? So any subset could be empty, it doesn't need to even have elements. Then the subfield of C generated by X is the intersection of all fields containing X. In your homework, you will prove this is actually a field, the intersection of all fields containing it. It's not a hard problem. Don't overthink it. Okay, great. We will have a notation for this because we don't want to write the subfield of C generated by X, always. And so what we'll usually write down, although we're never going to use because we use something slightly different, but what is usually the notation that's usually used here is these sort of Langle and Wrangle symbols. This is noted by this. Okay, so this is the intersection over all fields, alpha and A, F alpha, where X is a subset of F alpha and F alpha is a field, subfield of C. All right, that is nasty. That is not something that we want to compute with necessarily, right? This is something that is helpful for proving facts, not necessarily helpful for computation. Okay? Nevertheless, it is in fact a field, and this is the definition of the subfield of C generated by X. What this definition tries to accomplish is what should be the subfield generated by X? Well, it should somehow be the smallest field out there that contains X. And it turns out that this is sort of the right definition. There's an alternate definition that I'll give you here in a second. All right, so that's the first part of our definition. The second part is a notation we use more often. So we'll say that an extension, L over K, is generated over K by X if L is generated by the subset K union X. Okay? Right, so with the notation that we have up there, this is saying L is the smallest, well, is the subfield generated by the K, and then these elements X. All right, if X is finite, which will be the case almost 99% of the time, we say L over K is a finitely generated extension. Why? Because you take K and you throw in finitely many elements. So this is the type of extensions that we were looking at earlier, this q adjoin root 2, q adjoin I, and so on. And we write for this, L is K, and then parentheses X. And we will often say K adjoin X. Moreover, if we write X as X1 through Xn, then we'll often use the notation K adjoin X1 through Xn instead of K adjoin X. And that's the notation we've been using, well, when there's a single element at least. So let's just scroll up for a second here, and let's just verify that this is the notation that we were using before. All right, Q adjoin, where do we introduce? Q adjoin root 2 is I'm looking for the smallest field that has access to Q and root 2. It turns out that the right-hand set is that smallest field, but that this equality actually requires proof, and we will learn how to prove that here in a second. Not in this video, but in subsequent ones. Q adjoin I is I need access to Q and I. Okay, that's exactly what this is. And then F is, I just called this F earlier because I didn't want to burden us with notation, but properly we would call this Q adjoin, we have to add in I and we have to add in root 2. All right, so this is the origins of our parentheses notation. And in the next video, we're going to look at an alternate way of describing this, this field and prove some results on what to expect in the field.